Well, welcome to lesson 4 of chapter 7 on similarity in right triangles. And in this lesson, we are going to use relationships in similar right triangles. And as it turns out, we have some special things that are going to happen with our right triangles where we're going to have 3 similar triangles. Okay, so we're going to be specifically talking about the altitude. And in this theorem, it says the altitude to the hypotenuse of a right triangle. This is the altitude, segment CD. That's the altitude to triangle ABC. And that altitude will divide our big right triangle into 3 similar triangles. So we have the little one right here, ACD, and we also have the one down here, which is triangle BCD. And here are our triangle congruence statements. So ABC is similar to ACD, which is similar to CBD. Okay, so all 3 of those triangles are similar. So in this problem, it says, what similarity statement can you write relating the 3 triangles in the diagram? Well, that's going to go back to the theorem that we just stated. So we have one large triangle, triangle XYZ, and it has an altitude WY, so that altitude is dividing the triangle into 3 similar triangles. So it's always helpful to go ahead and try to draw those so that they're oriented the same way. All 3 triangles are oriented the same way. That makes it much easier to write our triangle congruence or triangle similarity statements. So we can see that triangle XYZ is similar to YWZ, which is similar to XWY. All right, so here's one for you to try. What similarity statement can you write relating these three triangles in the diagram? It's a right triangle with an altitude. And then from the similarity statement in part A, write 2 different proportions using this ratio. So first of all, our similarity statement will be triangle PQR will be similar to triangle SPR, which is similar to triangle SQP. I didn't break those up. You could go ahead and do that and break those up into the same positions to make sure that they line up. And then our part B, the 2 different proportions we could write, SR to SP. Well, if we just look at this middle one, SR are the 2 outside letters, so that will correspond to PR in this one. And then SP are the first 2 letters will correspond to PQ. So we could write this ratio right here, if I can get this one to come in. There we go. We can say SR is to SP as PR is to PQ. We can also say in the third triangle, okay, SR corresponds to SP and SP corresponds to SQ. So those are our 3 or our extended ratios that we could write involving those 2 segments. All right, proportions in which the means are equal occur frequently in geometry. For any 2 positive numbers a and b, the geometric mean is the positive number x such that this ratio is true. Okay, so the geometric mean, the reason we call it the mean and the other term is the extremes. So let me just show you this. I think I may have shown you this in class, but I just want to double check. So usually we have 2 proportions, A to B and then C to D, I guess we'll just call it. And the 2 on the inside here are called the means, right? And this may have been in a previous video. The 2 on the outside are called the extremes. So that when we write them as ratios in fractional form, the means are the ones on the inside, and the means are the ones that go along this diagonal. These are the means, whereas these 2, A and B, are called the extremes. So I just wanted to make sure that you understand what those are. So what is the geometric mean of 6 and 15? So first of all, we need to write our ratios using the definition of geometric means. So we would write 6 is to x as x is to 15. Remember, the x's are going to be our geometric means. And then cross multiplying, we get x squared is 90. So x is the square root of 90. But to simplify that, we can write that as x equal to the square root of 9 times 10. The reason we write it that way is 9 is a perfect square and will come outside of the radical. So the square root of 9 is 3, but the 10 doesn't have any perfect squares in it, so it stays in the radical. Here are two corollaries to our theorem that we just had. And in this one, this is a pretty powerful thing to be able to use. This one says that the length of the altitude to the hypotenuse, so the hypotenuse is AB, the altitude is CD, and it says that the length of the altitude to the hypotenuse of a right triangle is the geometric mean of the lengths of the segments. So over here, the geometric mean is CD. So it's like the x's were in the last example. They're on this diagonal. And then the numbers that are on the other diagonal are the two segments that make up the hypotenuse, AD and BD. Okay, so try to get yourself familiar with how to use that and write those. They give you an example down here. So 4, right here is the geometric mean. So you say 2 is to 4 is 4 is to 8. Okay, so that's kind of the pattern, 2 to 4, 4 to 8. So it's kind of handy to be able to use. This second one says the altitude to the hypotenuse of a right triangle separates the hypotenuse so that the length of each leg of the triangle is the geometric mean of the length of the hypotenuse and the length of the segment of the hypotenuse adjacent to the leg. Well, what does all that mean? Well, if we look at our original triangle here, what we have, the geometric mean is AC on this one. Okay, so it says this is our geometric mean. And then the other two numbers are the other leg, AB, the hypotenuse leg, the hypotenuse of the big triangle, AB, and then AD is the adjacent one to the geometric mean we're using. So the other one would be CB is the geometric mean. It's along this diagonal. So one of the ones will be DB, and then the other one will be AB, the whole hypotenuse. So here's one with the numbers with a triangle. So we have 4, the whole hypotenuse, is to 2, as 2 is to 1. Okay, it's the adjacent one. That one's a little more difficult to understand. Here is an example that might be a little bit easier, stated in a more simplified way. So the first corollary says this. It says the ratio of S1 to the height to the altitude is equal to the altitude to S2, which these are the two segments that make up the hypotenuse. S1 to A is equal to A to S2. That one's pretty easy. Now corollary 2 says the whole hypotenuse is to one of the legs as the leg is to the partial hypotenuse. Okay, that's adjacent. And the second part, the hypotenuse is to the second part of the leg as the second part of the leg is to S2. I think that's written a little bit more easily for us to understand. So let's go ahead and do some problems. What's the value of x? Write a proportion using that corollary. Well, a proportion would be the entire hypotenuse is to x as x is to 4. Okay. Simplifying that, we're going to do the cross product. And then multiplying across, we get x squared equals 64, and x is equal to 8. Okay, then on the other one, our proportion that we're going to write using y, okay, that one's going to say y, 4 is to y is to 12. Remember, y is the geometric mean. So now we just need to multiply across and simplify. And we get y equals 4 square roots of 3. This one is 48, which is 16 times 3. 16 comes out as a 4. All right, here's one for you to try. See if you can set these up and solve for x and y. I'll give you the solutions when you come back. All right, hope you gave that a try. Let's work on letter A for the variable x. You need to set up a proportion that will say the whole length of the hypotenuse is to x as x is to 4. And then multiplying across, we get x squared is 36, or x is 6. The value of y, this one's going to use the first theorem that we had. So we're going to say 4 is to y as y is to 5. And then multiplying, we get y squared is 20. But 20 has a perfect square of 4 in it, So that 4 is going to come out as a 2, and we get 2 square roots of 5. Alrighty, here's your lesson check. Go ahead and work on 1 through 6 here, and I'll collect those, or we'll talk about those when you come into class the next time. See ya!